In the previous video we talked about electric charge and how objects either have a positive electric charge or a negative electric charge or no electric charge. And it all comes down to the electrons and protons, and sometimes you can strip some electrons away, sometimes you can add some electrons and therefore make an object have a non-zero charge. We said that positive charge and negative charge will attract each other. Positive charge and positive charge will repel each other, and negative charge will repel each other. So opposites attract, but like charges repel. But we didn't talk about how big those forces are, those attractive and repelling forces. So that's what we want to talk about now. So the idea is to introduce the idea of an electric field, and this is just like gravitational field. So when we learned gravity, we learned that everywhere in the universe there is a gravitational field, and we called it little g, and it was a vector. And anything with mass contributed to it, and anything with mass felt it as a force. That's the gravitational force, right? So things with mass created an electric field, things with mass created a gravitational field around them, and then other things with mass felt that field as a force. So it's the same thing here. It's exactly the same idea, and in fact the formulas will take the same form. So now we're saying there is an electric field everywhere in space. We call it E, and it will be a vector. It does have a direction. And now instead of mass, it's charge. Any object that has electric charge contributes to the electric field around it. And any object that has electric charge will feel the electric field at its location as a force. Okay, so that's the idea. So there's everywhere in space there are picture these arrows pointing in of varying strength, magnitude. And if you put an object with charge in there, it will feel that electric field and it'll get pushed. Okay, so let's talk about this electric field, get to the details. So again, it's E. It is a vector, so it is a magnitude and a direction. So its units are newtons per coulomb. Newtons per coulomb. So you can see force, the force unit is here. So if we multiply the electric field by coulombs, by charge, we will get newtons. An equivalent one is volts per meter. We have not talked about volts, so I'm going to ignore this for the time being, but just in the interest of completeness, later on when we understand what a volt is, volts per meter is an equivalent unit. It's not a different unit. It's actually, 1 Newton per coulomb is 1 volt per meter. It's the same thing. It's just a different name. As we say, it's present at every location in space. So everywhere in space, you can imagine there's an arrow pointing in a direction with a certain magnitude, and that's just everywhere. Right? Okay. And the idea is the magnitude is, we scale it so that it's how strong a force a positive 1 coulomb charge would feel if it were placed there. Okay? Now, more coulombs will feel more force, and less coulombs will feel less force. But a positive 1 coulomb charge, that's how much force it'll feel. That's the magnitude of the electric field. So all you have to do is take your electric field and multiply by your charge. We use the letter Q for charge typically. You take your electric field and multiply by the charge, and that'll tell you the force. These are both vectors, okay? So that's the idea. If you multiply, if Q is positive, if your particle has positive charge, then if you recall how vectors work, when you multiply a vector by a scalar, it keeps the same direction. It just changes the number. So a positive charge feels a force in the same direction. But a negative charge, if you multiply, so Q can be negative here. If you multiply by a negative number, do you remember that the vector flips its direction? It's like 180 degrees in the opposite direction. So negative charges actually feel a force in the opposite direction. That didn't happen with gravity because you can't have negative mass, but you can have negative charge, so that is a possibility now. So what I'm saying is if you put a positive charge like right here, and let's say it's plus 3 coulombs, and if the electric field is as I drew it, then it will be 3 times that electric field, so it'll be in the same direction, just 3 times as big. That'll be the force that that object feels. If we put a, let's see, if we put a negatively charged object, so maybe -2 coulombs right here, where the electric field is going this way, then it will feel a force going in the opposite direction, because we have to multiply by -2. So, and it'll be twice as big, so it'll be something like that. That'll be the force that that object feels from that electric field, from the electric field at that location. Okay. All right. So again, just to summarize, a collection of charged objects, they create an electric field at all points in space around them. And then what we can do is we can compute the force, and we call it electrostatic force, by the way, electrostatic force due to it on any charged particle by multiplying the charge by the field. So this is our formula. So these charged objects, we consider them, they're like the source objects. They're the ones that are creating the electric field, or, modifying and contributing to the electric field all around them. And then we focus on one particular charged particle, and we think of that as the target. That's the one that we're going to see how it responds, how it feels. Of course, they all respond to the electric field. There's nothing special, but it's just we usually take one at a time and ask, okay, how is this charged particle reacting to the electric field that it is in? And then the formula is here. What I haven't done yet, and I will in a second, is start to tell you about this half of it, how the source objects create the electric field around them. I haven't given you any formula for that. Okay, but this is the simple formula that always applies to how an object reacts to the electric field that it's in. Okay. So, in an example, an object with a charge of -6.20 microcoulombs is in an electric field that points to the right and has magnitude 3 × 10⁸ newtons per coulomb. And so, if there are no other forces, what acceleration does it feel? I need to tell you the mass. Let's say that the mass of this object is 0.030 kilograms. Okay, let's see what happens. So we have, at this particular point where the object is, the electric field points to the right. And there's its magnitude. All right, so we have our object is right here. And so since it has charge, it will feel the electric field that at its location as a force. And it will be Q times E. So its Q, its charge, is -6.20 times 10⁻⁶. That's what micro means. Coulombs times 3 times 10⁸ newtons per coulomb. Right, so you can see that coulombs times newtons per coulomb will give us newtons. And we get sorry, counting zeros here. 1, 2, 3, 4, 5, 6, -1,860 newtons. So that's the force it will feel. All right, now that's one force. There could be other forces on this object, right? But if we want to know the acceleration, and if there are no other forces, then this is the only force. That's the net force, right? So then we can use F equals ma. So A is, since there's only one force, the sigma isn't really doing anything. Divide it by the mass. So just Newton's second law. So 1,860 newtons divided by 0.030 kilograms is going to be quite an acceleration. Yeah, 62,000 meters per second squared. that's the magnitude. So I should draw the picture. So our force is going this way to the left, right? Because it was negative, and it's the opposite direction of the way E is pointing. And the acceleration, of course, will be in that direction as well. So this object will be accelerated this way. Okay. Now, let's talk a little bit, or at least start to talk about where these electric fields come from. As we said, they come from point charges. They come from charged objects. They're the things that create the electric field around them. A single charged particle, which we call a point charge. So just think of a little guy, just a little particle that has some charge. It will produce an electric field, and here is the formula for it. It's a constant Ke. So Ke is this number right here. It's a big number. It's times 10 to the 9th newtons meter squared per coulomb squared. This is known as Coulomb's constant. So there we go. Times the charge of the particle we're talking about, divided by r squared. That's the distance away from the object. And this r hat means, and I forget if I think we used this when we were talking about gravity. It's completely analogous to gravity. This just means away from the particle. That's what r hat means. So we have this sort of like our origin, our particle, and this is just saying the direction. This is the magnitude, and this is the direction of the E vector. So like at a point right here, it's pointing this way. At a point right here, it's pointing this way. At a point right here, it's pointing this way. Right? Now, notice the divided by r squared. This is an inverse square law, just like gravity was. So the bigger r is, the smaller this will be. So if I go out further, it'll still point away, but it'll be considerably shorter. Right? If you're really close, it'll be a really big electric field. Okay, so that's the idea. And that was exactly like gravity. In fact, the formula for gravity, if you recall, the gravitational field created by an object with mass was a constant, big G, times the mass divided by r squared, and then I forget if I used this notation at the time, but r hat, basically, actually it was toward. In that case it was toward, so it would be negative r hat. They were all going toward, right? Because gravity is always attractive. But in this case, it's a repelling force, at least for same charge particles. Okay. So, but my point is, it's following the same format: a constant times the property, here mass, here charge, and then divided by r squared, inverse square law. And then either away from or toward the particle. So this is what any object, any small object, a particle that has charge, this is what it contributes, this is what it brings to the electric field. Okay, so we'll use this in some examples in the next video.